Okay, welcome to the third lecture in this series. This time we will be talking about Leibniz notation for derivatives, the idea of higher order infinitesimals, and more. The more, in this case, being our first example in which we will be able to take a specific function and figure out what its derivative must be. But before we can get to that, we need to talk about Leibniz notation, which is another notation for a function's derivative. Last time we talked about prime notation for a derivative, namely if we have a function y equals f of x, then we would denote its derivative by y equals f prime of x. And there are natural variants of this prime notation. For example, if, as we sometimes do, we refer to our function just simply as f, we might just call its derivative f prime and leave everything else out. Or, for example, if in other circumstances we refer to the function simply as y, then we might just call the derivative y prime. These sorts of variants are things that you'll encounter naturally, and you'll get used to them as you see them. But Leibniz notation is a different sort of notation for the derivative altogether. It can look a little strange when you first meet it, but as you'll see as this course develops, it's marvelously useful, and eventually it kind of does a lot of thinking for you. To explain what it is, I first want to remind you of something you have probably met before, either in earlier math classes or in science classes. It's your old friend, delta notation. I'm referring here to the capital Greek letter, delta, which is often taken to mean, in math and science, the change in some variable. For example, long ago you would have learned that if we have a linear function, such as the one graphed here, then the slope can be computed as the rise over the run. Well, how do we find the rise and the run? Well, we take any point, like this one, take any other point, like this one, and ascertain how much the x value has changed and the y value has changed between those 2 points. The change in x coordinate we call delta x, the change in x, and the change in y coordinate we call delta y. And consequently, we can write that the line's slope is delta y over delta x. And this already gives a hint of how this will be connected to derivatives, since derivatives measure slope or rate of change. Anyway, if x is some variable that has undergone a change, then delta x is defined as follows. It's x's value after the change minus x's value before the change. So if the value of x changes from 5 to 11, then of course delta x is 6. 11 minus 5 is 6. On the other hand, if x's value changes from 4 to 2, then delta x is minus 2, because 2 minus 4 is minus 2. The negative indicates that the change has been in the negative direction. Okay, nothing new here, but spelling this out explicitly should help us later on. Now let's connect this to derivatives. So, let's say we have a nonlinear function, like the one I have graphed here. And let's take a point in the domain of this function, like this one. And for the sake of argument, let's just say that is at the value 7. Well, we talked last time about the distinction between the function itself and the derivative of the function. Like if we asked, what is the value of this function at 7? Well, I'd need a scale on this axis, but for the sake of argument, let's say that when you put 7 into the function f, you end up with 6. So that we might say that f of 7 is 6. Well, what's the value of f's derivative at 7? That's not going to be 6, because the derivative is measuring the rate of change of this function around that point. So how fast it's changing if we restrict ourselves to an infinitesimal neighborhood so that this curve looks like its tangent line right there. And remember, the idea is that if we were to look at a little infinitesimal neighborhood, and again, when I say infinitesimal, I don't just mean very small like this is. I mean infinitesimal, smaller than any positive real value. But since I can't draw that way, you have to make do with this schematic drawing. Anyway, if we were to take this little infinitesimal region and think about what life is like there for an infinitesimal bug, where there is no distinction between the curve and the tangent line, then we can say, locally, this function, this graph, is linear. And therefore, I can talk about the slope, or the rate of change on an infinitesimal scale, in the local neighborhood of 7. And I might look at this thing and say, well, it looks like the slope here might be, I don't know, about 1.3, let's say. And consequently, we might write something like f prime of 7 is about 1.3. Good. This is all review. Let's see what Leibniz notation will do for us. I'd like to be able to say something like, oh, well, this is delta x and this is delta y, but I can't quite do that because delta x and delta y refer to a real change in x, a real change in y. These aren't real valued changes in x and y. This is on an infinitesimal scale. That means this is an infinitesimal increase in x, and this is an infinitesimal increase in y. So we have a special notation for that. Whereas delta x refers to a real change in x, and when I say real, I mean as in the real numbers, not like real as opposed to false. A slightly different notation introduced by Leibniz, dx, where this is a lowercase d, refers to an infinitesimal change in x. Consequently, over in my picture here, what I would write on my infinitesimal scale is that this side is dx, the infinitesimal change in x, while this side is dy, the infinitesimal change in y. So that we might write something like dy over dx is about 1.3 when x is 7. Of course, if x were some other value, dy over dx would be very different. It would be negative at the point I'm looking at right now. These two statements right here are telling us the same thing, and these are our two main derivative notations. If this one right here is prime notation, then this one right here is Leibniz notation. And while it may look unnecessarily complicated, it is actually the key to most of what we'll be doing this quarter as we develop our calculus of infinitesimals. It's what's going to allow us to actually get off the ground and take these intuitive ideas and turn them into a powerful calculus. I should also add that this symbol right here is usually just read aloud as dy dx rather than dy over dx. Not a big deal, but that's usually how you will hear people say it. And just as there are little variants in the way we might use prime notation, there are some variants with Leibniz notation as well. The simplest variant is a natural one. It's just where we would replace this y with the actual function f of x. So, for example, let's just say this point is when x is 4, and it certainly looks like the derivative of the function f there is 0. That being so, if I wanted to use this slight variation within the Leibniz notation, we might write this. d of f of x over dx is about 0. And of course, once again, we need to specify where this occurs when x equals 4, because the Leibniz notation doesn't really have a nice place to put the argument as the prime notation does. That might seem like a big disadvantage. It really isn't. One very nice thing about the Leibniz notation is that it always keeps right in front of your eyes what a derivative is. Whether we write it this way, or other ways that we'll see soon, reminds you that the derivative is a ratio. It's a rate of change. It's a ratio of two infinitesimal changes. A slope, a rise over a run, albeit carried out on an infinitesimal scale. Hence the special notation with the little d rather than the delta. One advantage of Leibniz notation is that it explicitly shows us the independent variable. Now, in many cases, it doesn't really matter because the independent variable may be obvious, but there are other cases, especially in scientific applications, in which the same output quantity, y, could be considered a function of several different independent variables. Prime notation doesn't help us there. Leibniz notation does. To show you what I mean, I'm going to return to an old example from the previous video. Let's go back to our example of the clock that we have wired to an oven. And let's say that capital T, the oven's temperature in degrees Fahrenheit, is a function of theta, the angle between the hands on the clock. And let us further specify that theta is measured in radians, and also that theta will be a value between 0 and pi. Thus, for example, in the picture here, theta would be this angle and not this angle. That is just to eliminate ambiguity. Okay, so we are assuming that we have arranged matters so that T, the temperature, is a function of theta, the angle. So if the hands are in this position, and let's just say theta is 2 radians there, or if the hands were in some other position where theta was 2 radians there, in both those cases, the oven would have the same temperature, because the temperature, we're told, is determined solely by that angle. Fine, but if that's the case, then it is also the case that the oven's temperature is determined by the time of day, because this angle itself is a function of the time of day. For example, if it is noon, then we know that the clock looks like this, and the angle theta is therefore 0, which in turn determines the temperature of the oven, whatever that may be. Or at 3 o'clock, the angle between the hands is, of course, going to be a right angle, pi over 2, and that is going to determine the temperature of the oven. So clearly, the actual time determines the temperature as well. And we could just as easily say that t is a function of, let's call it little t, where little t is a measure of time. For the sake of definiteness, let's say that little t is measured in minutes past noon. Not a whole number of minutes. This can be a continuous number of minutes. It could be 3.18724 minutes. It doesn't matter. But that's how we're going to measure t. So we can think of the temperature as a function of theta, of the angle, or we could think of it as a function of time. Now let's specify something about how the temperature varies. Let's suppose that the wider the angle, the warmer the oven. This is something we have arranged with our fiendish engineering as we hook these two things together. What I want to do now is to take this statement and translate it into a statement about a derivative. Now you might say, I don't see anything about derivatives here, but this is actually a statement about a derivative because it is a statement about continuous change. Derivatives are all about change, rate of change, how the dependent variable changes in response to little changes in the independent variable. Here we're told that the temperature, the dependent variable, is increasing. It gets warmer in response to changes in the independent variable, the angle. So whatever this function might actually look like, whatever formula might govern it, whatever its graph might look like, this condition imposes a serious constraint on it. If I tried to graph this function, for example, I know that I'd have theta on my horizontal axis and capital T on my vertical axis. And while I really don't know what the graph would look like, it could take all sorts of different forms, this condition tells me something about the graph. As the angle gets bigger, as I go further and further down the horizontal axis, the oven gets warmer. It goes up. That means that my graph can't ever go down or be flat. It has to constantly be increasing. Now, it might increase in different ways. It might look like this, or maybe it might look like this, or maybe it's some combination of the two. Maybe it looks like this. All of those examples, the function is increasing the whole way, so that the wider the angle gets, the more the temperature goes up. If the graph was ever decreasing, if it ever went down, even for a little bit, then this statement would be false. So I know the graph is increasing. For the sake of argument, let's just say it looks something like this. What does that strictly increasing function tell me about the derivative of my function, capital T, when I'm thinking of it as a function of theta? Well, the derivative is the rate of change, which in turn I can think about as the slope. If the function is increasing everywhere, that means its slope has to be positive everywhere. And if its slope is positive everywhere, that means the derivative of the function is positive everywhere. And if I'm talking about capital T as a function of theta, I can express the fact that that derivative is positive everywhere by writing dt d theta, that's the derivative of temperature with respect to theta, is going to be positive for all theta. I have to specify that because remember, the derivative just gives us local information. So this is just a consequence of this statement. Great! We're seeing how information about a function or information about its graph, that it's constantly increasing, corresponds to statements about the derivative, that the derivative is always positive. As you might imagine, if a function is always decreasing, the derivative is always going to be negative. More on this later. But I want to return to this second way of looking at the function, where we're thinking of it as a function of time. We might ask, what about dt d little t? The derivative of temperature with respect to time. Is it also going to be positive at all values at little t, at all times? I encourage you to pause the video for a few minutes and think about whether this will always be positive as well, or if it may sometimes be negative. Go ahead and do that now. Okay, I hope you did it. The sign of this derivative varies. It's sometimes going to be positive and sometimes going to be negative. Let's look at some examples to see why this is so. Let's say it's 12:15. Since little t measures minutes past noon, this would be at t equals 15. Well, at that time, what can we say about the derivative of temperature with respect to time? Well, what does this mean? This is a rate of change. We want to know whether this is a positive rate or a negative rate. That's all we care about. Well, a ratio is positive if the top and bottom have the same sign. So let's just imagine that at this particular time, we nudge time ahead by a little infinitesimal amount. So a little positive infinitesimal change takes place an instant after 12:15. So we've got a tiny infinitesimal change here. That is going to beget a change in temperature. If that little change in temperature, that little dt, is also a positive infinitesimal change, then this whole ratio will be positive and the derivative will be positive. But if that little change in temperature is negative, in other words, if the temperature of the oven gets colder in response to that little change in time, then we would have a negative infinitesimal over a positive infinitesimal, and this whole thing would be negative, and thus the derivative would be negative. Well, let's think about this. We make our little infinitesimal nudge. We increase t from 15 by an infinitesimal amount. What's going to happen? Well, the minute hand will move an infinitesimal amount this way, and the hour hand will move an infinitesimal amount that way as well. Although both hands are moving forward, this hand will move forward faster and the angle will widen. And since the angle widens, and we've said that the wider the angle, the warmer the oven, the temperature will increase by an infinitesimal amount as well. So we'll have a ratio of two positive infinitesimals, which means that this whole thing will be positive. And we conclude that at this time, this derivative is positive. Okay. But let's look at another time. This is around 12:40, or in other words, at the time t equals 40. And we want to know, at this time, what can we say about the sign of the derivative of temperature with respect to time? Is it positive? Is it negative? Well, let's think about it. We're going to increase, starting at this time, we're going to increase the independent variable, time, by an infinitesimal amount. Time has moved forward by an instant. What happens to the temperature? It's going to change an infinitesimal amount in response. But is it going to increase? Is this going to be a positive infinitesimal change? Or is it going to decrease? Is this going to be a negative infinitesimal change? Well, once again, the minute hand moves faster than the hour hand. Both of them are proceeding clockwise. Obviously, it's a clock. But the minute hand is moving faster. So it's going to be catching up. They both make tiny, tiny changes. The hour hand advances a little tiny bit, and in that same instant, the minute hand advances a tiny, tiny bit. But it's moving faster, and therefore closing that angle. It's a little smaller than it was before, which means that the angle theta is narrowing. It's getting smaller. But we know that the wider the angle, the warmer the oven. Or in other words, the smaller the angle, the cooler the oven, which means that that narrowing of that angle in that instant means that this infinitesimal change in temperature is going to be negative, which means that a positive infinitesimal change in time begets a negative infinitesimal change in temperature. And as everybody knows, minus divided by positive is minus. It's negative. So this is going to be less than 0. Interesting. So we have temperature. We can think of it as a function of theta, or we can think of it as a function of time. When we're thinking of it as a function of theta, that derivative is always positive. When we're thinking about it as a function of time, that derivative is sometimes positive and sometimes negative. It varies depending on the specific time in question. This is why it's often important not just to speak of the derivative of a function, but the derivative of a function with respect to a particular variable. This is one reason why Leibniz notation is so nice, because it gives us information specifically about the independent variable. Anyway, that's enough on the basic idea of Leibniz notation. I want to put it to use in calculating our first honest-to-God derivative. But before I can do that, we have to say a few words about higher-order infinitesimals. If we multiply a real number by another real number, of course, the result is a real number. This is true even if we multiply our original real by a tiny real. For example, if we start with a real number like 5 and multiply it by 10 to the minus 23rd power, we've just taken a tiny, tiny part of the original real 5. The result is still obviously a real number. Next, If we had taken our original real number and multiplied it by an infinitesimal, then instead of taking a tiny, tiny part of our original number, we're only taking an infinitesimal part of our original number, meaning that the result itself is infinitesimal. So once again, if I started with the real number 5 and multiplied it by an infinitesimal, dx, some little infinitesimal bit of x, then this product, 5dx, is itself an infinitesimal. It's an infinitesimal bit of 5. And we'll soon see how we can work with such things. Generally speaking, we operate with ratios of things like this, from which the infinitesimal bits ultimately cancel out, leaving us with something real. So we've seen that a tiny real bit of a real number is still real, whereas an infinitesimal bit of a real number is infinitesimal. But what about an infinitesimal bit of an infinitesimal? Something like this. Well, an infinitesimal bit of an infinitesimal is what we mean by a higher order infinitesimal. This product is to an infinitesimal what an infinitesimal is to a real number. These things are so absurdly small that when our concern is with real numbers, as it basically always is, we can discount higher order infinitesimals as though they were zeros. So for example, if in the course of our algebra we end up with dx dy, or say dx squared, dx times dx, or du dv, if we end up with expressions like these, all of which are higher order infinitesimals, we can just treat these things as though they were zeros. Now, how would such a thing ever arise in practice? I'll show you. Suppose we have a function y equals f of x. And given the formula for this function, suppose we wish to find the formula for this function's derivative. Well, how are we going to do that? Eventually, we'll have some theorems that will help us out, but for now, we have to rely on first principles. We have to go back to the basic meaning of what a derivative is. So we have to think to ourselves, if we were to take a value of x from anywhere in the domain of this function, here for example, we need to be able to determine the rate of change of the function at x, which of course we know is going to be measured by the slope of the tangent line there. And of course you know that it's very easy to find a line's slope if you know the coordinates of any 2 points on the line. Well, the problem here is that we seem only to know 1 point on the line. And its coordinates are, of course, x and f of x, since it's on the graph of y equals f of x. Well, if we somehow knew the coordinates of a second point on this line, it would be easy. We would just compute the rise over the run in the usual way. But in fact, we can find the coordinates of a second point. We just have to think infinitesimally. We know that locally, in the infinitesimal neighborhood of this point, the curve is straight. So that if we were to look at an infinitesimal neighborhood through our infinitesimal microscope, we'd see something like this. Now this point has x as its first coordinate, but suppose we were to take this point and increase its first coordinate by an infinitesimal amount, dx. Well, that change in x begets a change in y, if we're going to be back up on the tangent line, or the curve, which of course are the same thing on this scale, dy. What I want to do now is write down the coordinates of this point, and I'm going to do so in a way that is going to help us in a moment. Let's start with the first coordinate. Well, that should be easy. The first coordinate of this point was x, and then we added on a little infinitesimal bit, dx, which means that the first coordinate of this point is going to be x plus dx. So x plus dx would live infinitesimally close to x on this axis. I'll leave a little red dot there to indicate that that is supposed to be x plus dx. Okay, but what about the second coordinate of this point? You might say, well, that's just as easy. The second coordinate of this point was f of x, and now we've added on an additional dy, so shouldn't this be f of x plus dy? Yes, that is correct. But what I would like to do is to reduce the number of variables here. Instead of introducing y up here as well, I want to put it in terms of x exclusively, which I can do because I know this point lies on the curve, the black curve here, the graph of y equals f of x. Every point on this curve has the property that its second coordinate is f of its first coordinate. So that means this second coordinate is going to be f of x plus dx, the first coordinate. And writing this out will help us see a different expression for dy as we try to rephrase everything so it's in terms of x. To begin with, of course, we could say that dy is the same thing as d of f of x to indicate the specific function we're working with. And this represents the infinitesimal change in the function's output. Well, the function's output was originally f of x, and then after this little change in input, the function's output was up here at f of x plus dx. This change is going to be f of x plus dx minus f of x. So given d of any little function like this, you can always expand it into a form like this, and you'll have some exercises in the book to that effect. It's important for us because it gives us a nice way to express the derivative. Don't lose sight of what we are after here. We started with a function of x, y equals f of x, and we want to come up with some kind of procedure for finding the derivative of this function, dy dx. I now have enough information to do that. After all, dy dx, the derivative we seek, is just the rise over the run right here. And I can rewrite this dy dx as d of f of x over dx, once again just replacing the y with the specific function. And now I can take this numerator, this infinitesimal change in f of x, and expand it according to this little simple formula that we came up with a moment ago. The infinitesimal change in output is the output after the change, when we stick in x plus dx, minus the output before the change, when we just had x there. And this little formula we've come up with here is a recipe for computing a derivative from first principles. Now, as it turns out, there are only a handful of derivatives that we'll be able to compute from first principles using this recipe. But that will be all we need. Once we've got the derivatives of just a few functions, and we develop some auxiliary theorems, we'll be able to start combining things in such ways that we can take derivatives of more and more and more functions. But this will get us off the ground. I'll show you what I mean. Let's compute our first genuine derivative. So here's our problem. If y equals x squared, everyone's favorite parabola, find dy dx. Find the derivative of this function. Notice that I'm not asking you to find the derivative of this function at some specific point. I'm asking you to find the derivative as a function in its own right. Come up with an actual formula for this derivative function that will tell us, for example, that when x is 0, the derivative is 0. When x is 1, the derivative will be, well, some positive value. When x is minus 2, the derivative will be some other negative value, because the slope is negative there. Anyway, how do we find this actual formula? We're going to do it from first principles by using this formula right here. So here's our solution. The derivative, dy dx, is, in this case, d of x squared over dx, because y is x squared. Well, all we have to do is expand the numerator, just as we did over here. This is an infinitesimal change in the squaring function. We'll get the output after the change minus the output before the change, which is what these two terms up here represent. We're changing from x to x plus dx. This is the output after the change. This is the output prior to the change. Anyway, after our change, our first term right here, we'll be applying the squaring function not to x, but to x plus dx. So the first term up here will be the quantity x plus dx squared. And from that, we must subtract the output before the change. When our input was merely x, our output will be x squared, of course. And downstairs, we just carry the dx along. Well, this is a good start. Notice only x's appear here, which is good because we ultimately want to have some function of x. However, we do still have these pesky infinitesimals, which we will have to do something about. We don't want those in our final formula, of course. The infinitesimals are just scaffolding. We start with an ordinary real-valued function, and we should end up with an ordinary real-valued function. The infinitesimals will help us get there, but they shouldn't appear in the end. So anyway, how are we going to get rid of them? Some simple algebra will do the trick. There's nothing to be done with the denominator yet, but we can certainly expand this binomial as you would in an Algebra 1 class. When you do so, you get the square of the first term plus the square of the second term, plus the term that some students forget, which is twice the product of the two terms in the binomial. And of course we have to carry over the minus x squared. Okay, now what? Well, we have some cancellation. We've got plus x squared and minus x squared. And what about this term? Dx squared. Dx times dx. Ah, that is a higher order infinitesimal. It's an infinitesimal of an infinitesimal. And as such, we can treat it as a 0. So what are we left with? Dx downstairs, and all we have upstairs is 2x dx. And this is terrific because we have a factor of dx upstairs and another one downstairs, so they cancel out, leaving us with 2x. Hallelujah, our work is done. We have found that if y equals x squared, then the derivative of y with respect to x is 2x. That is, the derivative of x squared with respect to x is 2x. Good. Few points I want to make here. First, just a quick sanity check. Does this answer even make sense? Well, let's think about some of the things we expected to see. We said that when we had this function, y equals x squared, that its derivative at 0 should be 0. Well, if we put x equals 0 in, yep, the derivative really will be 2 times 0, which is 0. So that's good. And we said if we put 1 in, the derivative will be, well, some positive value. Well, here's our derivative. If I put 1 in for x, I get 2 times 1, which is 2, some positive value. That looks about right. And I also said if I put in minus 2, we'll get some negative value because we have that negative slope. And it's a steeper slope than it was when x is 1, so it should be stronger than 2. Well, if I put in minus 2 here, I would get a derivative of 2 times minus 2, which is minus 4, a very steep slope indeed. So this really does seem to check out. One more bit of notation, though. Expressions like this, we often write in a different way. We take the function and just kind of let it slip off of the fraction so that we would end up with something like this. Now that might look like a strange thing to do, but it's very useful because now I can think of this piece, the d dx right here, which is no longer a fraction because d all by itself isn't anything, but I can think of that expression d dx as what we would call the derivative operator. What's an operator? Well, it's kind of like a function, except whereas a function turns numbers into numbers, like the squaring function turns 9 into 81, an operator turns functions into functions. Thus, the derivative operator takes a function like x squared and returns another function, like 2x. There are some exercises in the book to help you get used to this sort of notation. It's common, we'll be using it just about every day for the rest of this course. And believe me, I sympathize. I know there's a lot of different notational variants that are thrown at you early on in a calculus class. You will get used to them, I promise. But you do have to be careful to try to use them correctly. Actually, while I'm here, if we wanted to state our conclusion in prime notation, we could do that in a couple of ways. We could say that if f of x is x squared, then f prime of x is 2x. Or even more directly, we might just write x squared prime is 2x. Very simple. You need to be comfortable with all the different notations, though. One thing I should point out is that it's generally considered tacky to combine Leibniz notation and prime notation in the same problem, so try to avoid doing that. I usually find that students gravitate towards prime notation in the beginning because it looks so simple. You just put that little prime there and voila, that's it. It's the derivative. Whereas the Leibniz notation has all sorts of different variations and it seems kind of fussy. But as I mentioned earlier, the Leibniz notation really can help us think. It may not seem like that at first, but you'll see this again and again and again as you go through your calculus courses. Here, for example, it led us to our first derivative. We were able to think of our derivative just as this ratio of dy over dx, write down different expressions for dy and dx, use what we know about higher order infinitesimals, and we end up with our derivative. Okay, I'm going to do one more example of computing a derivative from first principles, and it's going to be in some ways a silly example because we won't actually need calculus to find this derivative. We'll know what the answer is going to be before we start. But that way we'll be able to check ourselves and we'll be able to just focus on notation and process and things like that. So our new problem is to find the derivative of the linear function 2x plus 1. Note carefully, I am using this new notation, thinking of d dx as the derivative operator. Here's the function we're putting in. We have to determine which function we're going to get out. Well, as I said a moment ago, we actually don't really need calculus to know what function is going to come out. Because think about this function, 2x plus 1. It's a linear function. You don't need calculus to study linear functions. The whole point of calculus is that it allows us to study nonlinear functions as though they were linear, at least on a local scale. Linear functions are globally linear. So if I said, what's the derivative of 2x plus 1? That would be the function that gives me the local slope of this thing at any given input. Well, that's no mystery. If I take this as an input, what's the local slope here? Well, of course, it's the global slope, which is 2. If If I took this input, what's the local slope here? Of course, it's still 2. And if I took this as an input, what's the local slope? It's 2. That's the global slope. It's the slope everywhere. So I know before I do anything what this is going to be. The derivative of this function is going to be the constant function 2. It's a boring function. You put anything in the function and you get 2 out. What's the local slope at 5? Well, it's 2. What's the local slope at -2? Well, it's 2. What's the local slope at 0? It's 2. It's the constant function 2. So anyway, we know on obvious geometric grounds what this derivative is going to be. But I still want to carry out this process just so that we get used to it. It's kind of nice knowing what we're aiming at anyway. So here's our solution. To find the derivative of 2x plus 1, let's stick this thing back up in its perch so that we have a proper fraction. Like this. Now we've got a ratio of infinitesimals. All we have to do is expand the top according to our recipe. It's an infinitesimal change. That means we're going to get the function's output after the change minus the function's output prior to the change. The input changes from x to x plus dx. All right, when it's x plus dx after the change, the output of this function is going to be 2 times not x, but x plus dx plus 1. And from that, we have to subtract off the output before the change, when the input was just x. When the input is just x, the output is, of course, 2x plus 1. And as always, the dx just sits there. Now, let's massage the top here algebraically a bit. And when we expand all this out, we get all this stuff. I've just distributed that 2 and that negative, giving us this numerator, while dx bides his time in the wings. And now, of course, we get some cancellation. Plus 2x and minus 2x cancel. Plus 1 and minus 1 cancel. And we're left with 2dx over dx. And lo and behold, the factor of dx on top and the factor of dx on bottom cancel, leaving us with 2, exactly as we said we would end up with. And that's that. As I said, computing a derivative from first principles is something we'll only have to do a few times in the beginning, just enough to help get us off the runway. Once we're up in the air, with just a handful of derivatives, we'll be able to generate from them, and from a few structural theorems we'll prove, more and more and more derivatives, so that we won't have to get down to the nuts and bolts each and every time we want to take a derivative. Discounting this somewhat silly example, we've only so far really only come up with the derivative of a single function. We've proved that the derivative of x squared is 2x. But by the end of the very next lecture, we will be able to take the derivative of any polynomial in a matter of seconds. That's a huge step forward because, as you will see later in the year, just about any nice function you could ask for can be approximated as well as you want by a polynomial. So there is a sense in which once you understand polynomials, you understand everything. That's overstating the case. But polynomials are very, very supple creatures. They can mimic almost any function you want. All right, I think that's enough for this lecture. We've covered a lot of ground, and you need to do a lot of exercises before we can move on. See you next time.